All right, hi guys. We are going to walk through a couple of our homework problems. Just kind of go through the solutions as to how we got the answers for 9 through 11 and then number 15 looking at instantaneous velocity. So for number 9, I already created our graph here. So we've already done part A. Looking at part B, we want to write a model to describe this graph, including our units and our slope. So remember from chapter 1, for our model, we use y equals mx plus b. But instead of saying y, we're going to say what our y variable is, which in this case is position, and that's equal to our slope. And remember, we can find our slope by taking 2 points, finding the difference in our y values, and dividing that by the difference in our x values. So in this case, we're going to have 20 divided by 10 for a slope of 2. And then for our units, remember, we're going to do our y units over our x units. So that'd be 2 meters per second. That slope right there is going to represent the velocity with which our object is traveling. So for each second, our object travels 2 meters forward. Okay? And since we just have one line here, our object is going to have the same velocity for that entire time frame. All right. Then we need to multiply that by our x variable, which in this case is going to be our time, plus b or y-intercept, which we can see here is going to be 10 meters. And remember, our y-intercept, that 10, is going to represent our object's starting position. So here our object starts at a position of 10 meters. So now that we have that equation, we can use that in part C. So there is 2 ways that we can solve part C. Here we are looking for how far from the starting point was he at 6 seconds. So one way we could do this is, okay, so if we know we're traveling for 6 seconds at a velocity of 2 meters per second, we can do some dimensional analysis to find that he traveled 12 meters forward. Another way we can solve for this is by plugging that 6 into our equation. So we could say our position is equal to 2 meters per second times 6 seconds plus our original 10 meters. When we would do this, we would find that our new position after 6 seconds is 22 meters. However, we want to find how far he is from the starting point. So our final position is 22 meters, and our initial position was 10 meters. That means he traveled a distance of 22 minus 10, or 12 meters. So there's 2 ways we can solve this. We can either use our dimensional analysis, say, we know he was traveling at 2 meters per second for 6 seconds, or we can plug that time into our equation for position, and then subtract that from our original starting point, because that equation is going to tell us our position of our object, or in this case, Mr. Estabrook, at certain times. Looking at number 10 then, again, so here Mr. Estabrook is once again rollerblading, but here our data is a little different. So we already plot and labeled our position versus time graph. So for B, we want to find how far he is from the starting point at t equals 5 seconds. So before we can find how far he is, we need to find how fast he was going, or our velocity. And our way to do this is going to be by finding our slope. So we again can take 2 points, find the difference in our y values, and divide that by the difference in our x values. And we can find that our slope, or velocity here, is 3 meters per second forward. So for every second, he travels 3 meters forward. Okay? So if we want to find how far he's traveled at 5 seconds, what we can do is we can do our dimensional analysis. So for 5 seconds, he traveled 3 meters per second. So that means he's going to have traveled 50 meters ahead. Okay? If we wanted to, we could also write our equation for this line and then subtract our new position from our starting position, like we did in our previous problem. Okay, but either way, we should get 15 meters. So then for C, when we're trying to find our average speed, we know that speed is equal to distance over time. So when we're looking at distance, we're just looking at total ground cover. So remember, for distance, we do not care about what direction we are traveling. So if we look at this one, we started at 4 meters and we went up to 34. So that means this object traveled a total distance of 30 meters in a time interval of 10 seconds. So in this case, our average speed would be 5 meters per second. Okay, so what this tells us is each second our object is traveling 5 meters in any direction. That is different than our average velocity because our average velocity is going to take into account the direction that our object is traveling. Okay, and we're going to find average velocity by doing displacement over time. Remember, for displacement, all we care about is our initial position and our final position. So here, if we started at a position of 4 and ended at a position of 34 in 10 seconds, that would tell us our average velocity is a positive 5 meters per second. So what that tells us is every second our object is traveling 5 meters towards its final position. Okay, so average velocity, we're taking into account what direction we're traveling. In this example, our average speed and average velocity are the same, and that's because our object is only traveling in the positive direction here. It's not moving backwards at all. Okay. So then looking at D, in the first trial, he was further along at 2 seconds than he was in the second trial. Does this mean he was going faster? No, because if we look at these, remember our slopes tell us our velocities, and in our second trial, our slope was 3 meters per second, whereas our first trial, our slope was only 2. So we can actually see that he was traveling faster in that second trial. The reason why he was further ahead in the first trial was because he had a head start, or a greater head start in the first trial. So if we look at the first trial, he started at a position of 10 meters, whereas in the second trial, he started at a position of only 4. So that is why he was further ahead in that first trial, not because he was traveling faster. Okay, so then 11, we're looking at the final trial of Mr. Estabrook. So again, we've already plot and labeled our position time graph. So then for B, we want to explain what is happening in the time interval of 4 to 6 seconds. So before 4 seconds, looking from 0 to 2, Mr. Estabrook is traveling in the positive direction. Okay, because our positions are becoming more and more positive. They're increasing. 4 to 6 seconds, our position does not change, so he is going to stop. Okay. However, if you look at 6 to 12 seconds, here our positions are decreasing. Now that means he's traveling backwards or in the negative direction. So we can see before 4 seconds, he's traveling forward. After 6 seconds, he's traveling backward. So that means he stops to turn around, because our direction is after our 6 seconds. Okay. So then for C, what do you think is happening in the interval 6 to 12 seconds? We've already said he's traveling backwards. And if you look at this, he's getting closer and closer to the origin, which is where he actually started. So in 6 to 12 seconds, he is moving back towards his starting position. Because initially he was at a position 0, and from 6 to 12 seconds, he gets closer and closer to a position of 0 until he eventually gets there. All right, so then for D, we're looking for our average speed. And remember, for average speed, we do distance over time. Remember, distance, we do not care about what direction we are traveling. So if we look at our position time graph, from 0 to 4 seconds, he started at position 0, went up to a position of 12, so he traveled 12 meters. From 4 to 6 seconds, he stopped, so there he traveled a distance of 0 meters. And then from 6 to 12 seconds, he started at a position of 12, went to a position of 0, but here again traveled 12 meters. We don't care that it's negative because distance is not taken into account direction. Okay, and that's all over a time interval of 12 seconds. So when we add these up, we can see that our average speed can be 2 meters per second. So each second, Mr. Estabrook is traveling 2 meters in any direction. Okay, because remember, speed doesn't tell us what direction we're moving. It's just telling us how much ground we cover per second. And that is going to be different than our average velocity. So when we look at our average velocity, we're going to do displacement over time. And remember, displacement, all we care about are our initial position and our final position. So if we look at our final position, Mr. Estabrook ended at a position of 0, and he started at a position of 0. Since he ended at the same place he started, his total displacement is going to be 0 meters. And that was over a time of 12 seconds. So that means his average velocity here is going to be 0 meters per second. So each second, he's having an average velocity of 0 meters back to his starting position. All right, then the last one we're going to look at is number 15, because here we start getting into the term instantaneous speed. Remember, instantaneous speed, that is going to be our speed at a specific time. Okay? All right, but we're starting with letter A, where we're looking at our average speed. Like we saw with Mr. Estabrook, our average speed is always going to be distance over time. So we want to see how much ground this object covers from 0 to 12 seconds. So we can see from 0 to 4 seconds, he's going to travel 20 meters. 4 to 6 seconds, position's not changing, travels a distance of 0. 6 to 9 seconds, here he again travels 20 meters and going from 20 to 40. And then in 9 to 12 seconds, he is traveling 20 meters again, going from 40 back down to 20. And that's all over a time frame of 12 seconds. So now our total distance that our object traveled here is 60 in 12 seconds. So that means our average speed, oops, I should not have that positive sign there, since speed does not tell us direction, 5 meters per second. So each second, our object is traveling at an average speed of 5 meters in any direction. That's looking at our entire time interval. However, when we're looking at our instantaneous speed, here, we're just looking at it for 3 seconds. So we're looking at this point right here. So all we care about is how fast our object is traveling at this point. So we know we can find our instantaneous speed by finding the slope of the line that that point is on. Okay, so we are going to find the slope of the line from 0 to 4 seconds, since it includes that 3 seconds. So in this case, what we'll do, we know our slope. We can pick 2 points. We can find the difference in our y values. So 20 minus 0 divided by the difference in our x values, so 4 minus 0. And we should find our instantaneous speed. There is going to be 5 meters per second. Okay, because of the slope of the line that contains 3 seconds is 5 meters per second. However, when we look at C, our instantaneous speed at 5 seconds, it's going to be right here, we can see at that point our line is flat. That means our slope or instantaneous speed at 5 seconds is going to be 0. Our object is not moving at 5 seconds. Okay. All right. And then the last one we are looking at is going to be at 8 seconds. Like about right there. Okay. So looking at this one, we want to find the slope of the line that 8 seconds is on. Okay. And in this regard, we're going to pick 2 points again. So like 6:20 and like 9.5:40. I'll find the difference in those two y values. So 40 minus 20 divided by the difference in our two x values there. So at 40, we're about 9.5, and then at position 20, our time was 6. And when we plug that in our calculator, we should find that our average speed here was about 5.71 meters per second. All right, so the main thing that we see here is that our instantaneous speed is our speed at any specific time interval. And the way we can find that is by finding the slope of the line that time is on. Okay, we don't care about what's going on in the rest of our graph. We're just looking at the line that contains that point. So we know at 8 seconds, we're traveling at a speed of 5.7 meters per second, even though our average speed over the whole time interval is 5 meters per second. Okay? So notice how our average speed is not just an average of our individual instantaneous speeds, because we're traveling each instantaneous speed for different amounts of time. All right, if you guys have any other questions on the homework, please do not hesitate to reach out and I'll be happy to help. Have a great day.